Okay, we might as well get started. So today we're going to look at some arbitration policies and also a quick look at the next lab, which starts, I think, 1 hour into the session today or tomorrow, depending on what you're doing. So what we were talking about last time about n input arbiters, where n is the number of requests. So we have request line 0 labelled up to n minus 1, and you assert a request for a shared resource by putting a 1 on those request lines. You wait then for your corresponding acknowledged line to be 1. Once that arrives, you can then go ahead and use the shared memory or the system bus, whatever the shared resource is, and only one acknowledge should be asserted at any time. Once you've finished with the shared resource, you then drop your request line to tell the arbiter it's now free and can be allocated to another request. So what we're going to look at today is how do we resolve multiple simultaneous requests. So there's a conflict often. You need to resolve that in favour of one request over another. And how does that work? Well, that's called the arbitration policy, which is, here we are, here. So that's where we're up to in the notes. So there's different policies, and we'll look at the simplest one first. Then we'll go through an example of how this would work in practice, and I'll get you to draw the timing diagrams for request acknowledge for different policies. Then we'll go on and talk about how we would implement this in a real system. And in the lab, you'll be using that with 2 shared memory CPUs that access SRAM. Okay, so that is something you'll be doing in the lab. So the simplest approach is called fixed priority. So we remember you label the request 0 up to n minus 1. So what we're going to do here is just allocate it to the highest priority request that's active. So that's called a fixed priority order, and typically we'd start with request 0 as the highest priority and so on. So you just label the requests in order of the priority. So that's fixed priority, and then there's the problem with fixed priority is you may find the highest priority request may ask for the resource quite often, and that locks out other requests from accessing that resource. So there's a problem with hogging of the resource if a high priority request is pretty persistent about re-requesting for that resource. So round robin tackles that problem by rotating the priority on each acknowledge cycle. So the first one you may allocate to the same order of priority as fixed priority, but on the next allocation you would rotate that priority so the second request then has the highest priority, and so on. So that then shares the resource more fairly in principle. Another approach is you collect together all pending requests. When the resource becomes free, you then fix that set of requests. We call that a batch. So you might have, say, several requests waiting to access the resource. You then service those requests to exhaustion without considering any further requests, and you do that in a fixed priority sense. Okay, so that batching just locks out further requests until we've sorted out the current pending requests. And then once the resource is free again, after that batch has been allocated in turn, you then collect a new batch of requests. So we'll look at an example of that shortly. Finally, we'll look at first come, first served, which is the optimum strategy in the sense that it's the fairest, and that's the way often traffic works and people line up in a queue. That is first come, first served. So the first request should be serviced first, and the second, and so on. So that achieves a minimum variance of waiting times of any of the policies. You can prove that theoretically. Independent of any other distributions, first come, first serve allocates the resource as fair as possible. We'll look at some expensive, well, there's no cheap way to do it, but you can implement this strategy in hardware, but it is the most expensive strategy to implement. So we'll come back to that later. Okay, so we're going to get you to think about some tutorial problem style problems here. And this is a simple system, and we have some pretty simple constraints to help you just tackle the policy issues rather than the actual details of implementation. So we have 3 requests. This is sufficient to get the idea of what's happening. And we label them as we did earlier, 0 up to 2, and so n in that case is 3. So a request will allocate its request by asserting a 1 on its request line. And once it's granted, that means it has an acknowledge, and it then accesses the resource, so it only does that for 10 nanoseconds. So after 10 nanoseconds, the request should drop once the resource has been allocated for 10 nanoseconds. All right, so we're going to initialize the timing diagrams with request 0 and then follow up with the other requests a bit later on, and you'll see that shortly. And then each request will apply a new request after waiting 10 nanoseconds. So there's only 2 requests from each of the 3 requesters in this example. So what you're going to try and do now is complete the timing diagrams. And in that process, we're going to assume negligible logic delays and decision times. So you're not going to focus on the delay through the logic circuits, nor how long it takes to resolve conflicting requests. You just assume that that is done very quickly, just for simplification purposes. Okay, so let's get started here. This is the setup that we just described. So request 0 is asserted at time 0. So that's done with a 1 on the request line. And so the arbiter initially will just see a 1 on request 0, 0 on request 1, and 0 on request 2. That's what it sees. And you're going to act as the arbiter. So what your role is to complete the outputs of the acknowledge, okay, and that will impact when the requests can request again. Okay, so what we see initially is the arbiter is idle, so there's no request active and there's no acknowledges active. That's simple. So in a fixed priority, we have the priority order is request 0 followed by request 1 followed by request 3. So whenever request 0 is asserted and the resource is free, you need to allocate it to request 0. And if request 0 is not active, then you look down the chain through the priority. Okay, so have a go at this. So I want you to work out what happens. Let's just do the first part through interaction. So we have request 0 and you have the acknowledge 0, so that means acknowledge 0 is equal to 1. So that's what this is referring to. Obviously only one acknowledge will be asserted at any one time. We're just going to label that acknowledge as a number in that location. Okay, so what's the next transition in this system? Can anyone tell me what will happen next? In other words, which of these signals, request 1, 0, 1, 2, 3 and acknowledge which changes next. So request 0 change. Can you explain why that happens?
Because we are processing one request for 10 nanoseconds.
Correct. Okay, so we have a service time, as it's called, for 10 nanoseconds, so we drop the request once we have the resource for 10 nanoseconds. So that's what happens here. Now once that happens, the arbiter now has to allocate a new acknowledge. So I'll leave that for you to do, but let's just remember that we will allocate a new request after waiting 10 nanoseconds as well. Okay, so we can fill that much in, and I'll get you to think about what happens next. Yes, correct. So once the request is dropped from 0, then we need to allocate to the next priority, which, as you said, is request 1. So that would be shown here as a 1. Okay? All right. So just have a think about that. Hopefully you can sketch through the timing and then we'll discuss them quickly. Okay, so does anyone... Yeah, maybe we'll just go around the room and people can tell me what happens next in terms of transitions. So someone over here. So we've got request 1 has been acknowledged. This one here says, all right, acknowledge 1 is 1. Request 1 can now access the resource. So what happens next? Yep. And then we'll re-request. Okay. Okay, so that's an interesting point. So what we have now is a rising edge on request 0 and request 2 is 1. So what you're suggesting is we give it back to 0. Okay, there is a slight dilemma here, isn't there, in that does this transition here occur soon enough for the arbiter to make that decision? And we're going to assume yes, because there's minimal propagation delay in our logic. So that's really a bit of an assumption there, and it's a bit of a race condition in the sense. Maybe it does, maybe it does not catch that 1 on request 0, but let's assume it does. So that then allocates the output acknowledge of 0 becomes a 1, and again request 0 will drop here. Okay, so the assumption is we only do this twice, just to make it simple. All right, can someone else help me with what's going on next? You two have had a great turn, thank you. Maybe someone else would like to contribute. Or ask a question even if you wish. All right, so we have request 1 and 2 and you think it should go to 1. Yep, I agree with that. So it's the same situation as we had earlier, except we're resolving between 1 and 2, and we're going to give it to 1 because that has a high priority.
Why are we not going to request 2 after like 0 and 1?
Can someone answer that? Why isn't it request 2? Right, so request 2 is the lowest priority, and request 1, when it's asserted, will override request 2 because the priority.
And request 2 is 1, then only we will consider.
That's right. So you have to, request 2 is unfortunate. It has to wait for both the higher priority requests to be 0 before it will get the resource. All right, so finally request 1 will drop, and it's at that point that what happens? Okay, good. So request 2 then finally gets its day in the sun, and that's taken quite a long time, as you can see. Request here, and it finally gets it happening at 40 nanoseconds, so there's a delay of 35 nanoseconds, which is not too good. If you request 2, it really chokes up the system if you're trying to be fair about resource allocation. Okay, so request 2 will last 10 nanoseconds, and what you notice next is another issue in terms of throughput performance. What's happening in the next cycle here? Is the idle again. All right, so this guy re-requests, and then we're done. All right, so what we're noticing is this is not fair. Request 2 had to wait a long time, and then not only that is the idle state here occurs when we should have really been doing something with that shared resource. So that's not a great outcome. It's not particularly efficient in terms of resource usage. So that leads to the next policy. We hope that the round-robin policy will fix these problems. All right, so let's have a think about this. So round-robin has the property that we rotate the priority. So let's just write the priority order as another set of notes, if you like. So we're going to start with the traditional 0, 1, 2 priority order. And whenever we allocate the resource, we're going to rotate that priority so it becomes someone else's turn to be high priority. So what you notice, of course, is we start off the same way because it's 0, 1, 2 is the same as we had earlier. Once we allocate that, the priority changes to 1, 2, 0. Right? So nothing much has changed really since the previous example. So request 1 is now serviced here. So that gives us 2, 0, 1 as priority order. Okay, is everyone following that? Yep, good. All right, so what happens next? All right, so request 2 now has a turn, which is different to earlier because we had to wait for quite a while with request 2. Okay. So finally we go back to the original priority once we allocate the request 2. All right, so next one is 0. So 0 is now done, and we can then rotate the priority and give the next guy is a choice between 1 and 2, but you'll note 1 has higher priority in that case, so we'll give it to 1. And then finally we are left with 2. All right, so that's a really good outcome because request 2 now doesn't have to wait very long and we don't have an idle state that we had earlier which occurred here. All right, so this idle state at 50 nanoseconds is no longer there, so we have more efficient use of the system. All right, so that's a big tick. But round robin is still not perfect because if you're unlucky with regard to this rotating priority in terms of when you request, you still may have to wait for your turn to come around. Could be quite a while in a large number of requests. So that's not perfect, but it's certainly a big improvement. Okay, so batch priority is often a bit confusing because you've got to keep track of the batches. Alright, so if you look at the way this works is we collect all the active requests together when the resource is being used. So we keep collecting them, and as soon as the resource is free, we then allocate among that batch in a fixed priority order. Okay, so what happens here is we have a batch. Let's just keep track of what's in our batch. As soon as 0 requests, the batch contains just 0. The other 2 requests are inactive. Alright, so in this case we're going to allocate within the batch in a fixed priority. So that means we allocate to 0, and that has its 10 nanoseconds. Alright, so once the request drops here, we then have to work with a new batch of requests, which is what? One and two, that's it, yeah, not complicated. But what you notice is 0 is not in that batch. Now we must complete allocation to the entire batch before we move on to a new batch. So that's the way we can achieve some fairness in that. So we know 0 comes along later on, but we're going to ignore that until we've completed the entire batch. So now we're going to allocate to 1 and then 2, because that's the order within the batch. So we've allocated a 1 there and 2. Okay. So we have another new batch to consider, which is what? Anyone tell me? Yep, 0 and 1. Okay, 0 here and 1 here. So, yep, we've got 2 pending requests that have been waiting while the other servicing was occurring. Okay, so we have to service those in order of priority, which is fixed. Okay, now 0, yep, that's fine, it's finished, and 1 is also finished. And while they are being serviced, 2 is asserted, and that becomes a single request batch. And that becomes finally serviced here, and then it's idle thereafter. Now what you notice is we've got exactly the same result, 0, 1, 2, 0, 1, 2 in terms of the ordering of acknowledges. But as I said earlier, if you have a larger number of requests, then you find that the problem with batched arbitration policy is the top 2 requests will share the resource equally, and then the others have to fill in the gaps, if you like. So if you notice here, if request 0, for example, is pretty persistent and keeps re-requesting, then it's going to get serviced every second batch, okay, because it's the top priority. And those other batches, request 1 will be serviced at the start of the other batches. Okay, so you'll find that request 0 and 1 can have a higher allocation than the other requests in a more complex situation. All right, so let's move on to final one, which is first come, first served. So this one's particularly easy for us because it's natural. It's what you do every day, so we should be able to race through this one. Okay, so 0 occurs first, so we service that first, so that's easy. And then there's a dead heat between 1 and 2. So that becomes arbitrary. You can do that in either order. Okay, so there's actually 2 solutions here. You cannot separate 1 and 2 in their arrival time according to this ideal timing diagram. So let's be a little bit unusual here and put a 2 in there just for interest's sake. So then we have the situation shown here. So every time we need to do a new resource allocation, we look back at when the requests were made. So we have this situation here. We look back, is it request 1 or 0? Well, obviously request 1 is the oldest, so we need to service that first. So that would be a 1 there. Okay, so once that's complete, we look back again, and 0 is the oldest request here. So that would be done. And then followed up by 2. And then finally 1. All right, so that's the way that could have worked, but it could have flipped the other way. We could have actually changed that one to a 1, and there's just a tie there, so we can't separate them in terms of order of arrival. So either is acceptable with first come, first served. If there's a tie, it doesn't matter how you allocate that. I mean, you could actually do a round robin on the ties in terms of priorities, but that's getting a bit too intricate. Okay, so in the lab, you will be just dealing with a simple case of 2 CPUs. So the arbitration logic's not going to be that difficult compared to what we described, but nevertheless, you can see in more general situations where you have a system on a chip type architecture where there's literally could be thousands of CPUs on the one chip and they want to access resources, then you really need to think about this policy carefully in terms of the overall system performance. All right, so in the second bus control arbitration lab, you are dealing with memory as well as the 32-bit data bus. So the interface of the memory, it's an SRAM static RAM chip. It's a 16-bit data device. So the structure's a little bit different from the bus, and we're going to use 32-bit bus width on the Avalon bus bridge, but that has to meet up with the SRAM, which is 16 bits. So that's called a bus width matching problem. So the bus is giving us 32-bit words, and we're going to process them in 16-bit chunks for the memory. And part 2, we're going to have 2 processors sharing that same SRAM with an arbitration circuit. And there'll be 2 versions of that. The first one you would implement would be fixed priority, and then you may consider something fairer afterwards. Okay, so let's look at what this means. Hopefully you're becoming quite familiar with this environment. When we're interfacing to a 32-bit data bus, it's a little bit different to your experience with the 16-bit data bus. So obviously we're going to have 32 bits of write data produced by the bus bridge, and then the read data you need to define in terms of your bus interface logic is 32 bits. And by the way, it doesn't matter what you do with those 32 bits if they're not being read, if you follow that logic. So if you are doing a single byte read on the bus, in other words, 1/4 of the 32 bits, you can do anything you like in terms of what you write or what data you put on the read data lines that are not being used. Okay, so what that means is you don't have to worry too much about garbage that you put on the bytes that are not being read, because the bus bridge will totally ignore that. Now, why I'm mentioning that is it just simplifies things if you don't have to worry about the byte-enabled bits in terms of the read actions. Okay? So if you then just produce a full 32-bit value and only 1 byte of that's used, so be it. Doesn't matter. Okay. So what we're trying to do here is simplify the logic, but understand what is required at the same time. So in terms of the address that's produced by the bus bridge, it is always word aligned. So in this case, it's aligned to 32 bits. In terms of the word size. So the way that works is we allocate address bits 1:0, the lower 2 address bits, to what? To achieve that word alignment. To 0, 0. All right, so in the first lab you had the low order single bit of the address was always 0. It's an even address. Here we have an address that's divisible by 4 because you're operating on 4-byte words. So the bus bridge operates in terms of word alignment, and so does the processor as well. That's why they do this. So that means our byte enable has a size of 4 bits. Okay. So that's becoming a little bit more interesting, hopefully. Okay, so let's look at the problem of bus width matching. So you can divide this up into read-write cycles. When we do that, we've got our 1 32-bit word, so you might be doing a load word instruction with some operands. So that tells us we're operating on a 32-bit word rather than a load H, which is 16 bits, or load byte, which is 8 bits. Okay, so we end up with 2 16-bit SRAM read-writes required because the SRAM is 16-bit words. All right, so that means we're going to do it in 2 parts. You do the low half first, typically, followed by the high half second. When I say low half, that's the low address half, so the number of the address would be less than the address of the high half. Okay, so that's in terms of what the SRAM will see. So in terms of what we're doing with a full byte, we'd start off with the base address from the bus bridge, and the second in terms of the base address plus 1, 0 in binary. Okay? So the address going to the SRAM is always even, but we're going to add that offset to go to the 16-bit increments. So when this happens, of course, when you're dealing with the logic, you need to remember where you're up to if you are a logic circuit, and that involves storing some state value. And the state needs to reflect whether you're in the first or the second stage. Are you writing or reading the first 16 bits, or are you doing it with the second? Okay, you need to remember that because it affects where you put the data or where you write the data. Okay, so that's all you need to keep track of. Very simple. So this is now a sequential logic circuit, obviously, if you have a state that is keeping track of this information. So the question is, how many flip-flops do we need to store this information? So you're all thinking, oh, I've got to design this horrendous finite state machine with thousands of flip-flops and states and transitions. Well, no, you don't. So how many flip-flops do you need? How many? 5. It's an interesting number. Is that because it's 2 to the 5th number of bits, maybe? Well, the answer is actually in the previous point. Here is your answer. So we only have to store this differentiation between the first and second stage. So that tells us we only need 1 flip-flop. Okay, if it's 1, then we're in the second stage. If it's 0, the flip-flop output, we're in the first stage. That's it. All right, as I said, it's not complicated. All right, so this circuit has a single bit state, which is that flip-flop, and it just needs to use that state to determine are you doing the first or the second stage. Okay, so let's look at an example. This is a 16-bit SRAM interface to a 32-bit Avalon bus, and we're doing a LDW, which is load word, into R7 of the address 8 plus whatever's in R2. All right, so that is an address of what? Okay, so this is obviously a read transaction. We're going to issue the read bus signals in green. That comes from the bus bridge. The red is going to be from the SRAM. Okay, so that's what's being driven back into the bus bridge. And the black are the SRAM signals that we need to keep track of to do our work. Okay, so has anyone worked out the value of the address? All right, I think we've got the answer. 20 plus 8, 28 in decimal. All right, so that's going to be sitting here for a little bit, because you've got to do at least 2 cycles here of your timing. Right, so the bus enable, of course, will come out as a 1. And we're doing a read or a write? Read, yep. What about the byte enable 4 bits? What do you think that should be in this example? Yeah, 1, 1, 1, 1, 1, 1, 1. 4 ones, yes. So that's, of course, in binary. All right, so now you've got to think about what's actually happening to the SRAM device. Remember, it's 16-bit word. We've been told up here that at memory location 28 we have a 32-bit value, 4 A's, 4 F's, so that's in hexadecimal. So if we look at that carefully, maybe we should look at this. So at address 28, what would you see as the byte value of that address? We'll look at the other ones shortly. Just so you understand this, what would you see at address 28 as the byte value? Because addressing is byte referenced in terms of all convention in memory. Yep, this is in hexadecimal. All right, so you would see 0, 1, 0, 1, 0, 1, 0, 1. All right, 8 bits, which is 5, 5 hexadecimal. All right, 29, what would you see? Okay. Is everyone following this? If you're not, I need to know. So in memory, the addresses refer to bytes, so a 32-bit word will occupy 4 bytes, and what we're just elaborating is what you see in those 4 bytes. And this is important because we need to know this when we're doing the read timing. All right, so if we assume that we're going to get the low order 16 bits first, that's these guys here, then you would assume we would see this appear on the read data at some stage. So we'll do this in hexadecimal, but we expect to see from the SRAM the 2 bytes, the 5555 bytes appear, because that's the first read transaction from the SRAM. So what about the acknowledge? Does that go high here or not? Yep, does everyone agree with that? Because it's not right. Why is it wrong?
The acknowledge can be triggered after setting all the signals.
So who's reading the acknowledge line? Yeah, the bus bridge or the CPU, yeah. So this is saying to the bus bridge or the CPU, okay, we've got all the data finished, it's all available, the 32 bits has then been made available on the read data line. But clearly that's not the case, because we've only got the lower 16 bits in the first clock cycle. So this is still going to stay 0 here. All right, so what we expect to happen is the SRAM will produce 16 bits followed by the next 16 bits. So on the second cycle we want to see the AAAA and the other bit should be still there, and that's when the acknowledge is counted as 1. It can then read back that read data back to the CPU. So that happens on this rising clock edge. Okay, so that's pretty easy. All right, so this bit, the next bit's not so obvious, but let's try and do it. So now we're going to look at the SRAM, which has address lines coming in. This is a 16-bit word RAM chip. So its address lines are accessing 16-bit words. It has a high byte and low byte enable as well. So you can look at only writing, say, a byte in the upper or lower position of that word. But fundamentally, it's a 16-bit word SRAM. All right, so can anyone tell me what address you would send to the SRAM first up? All right, we've got the 28 decimal on the bus bridge. But now we've got to send this on to the SRAM. And we want to do the low byte first. This guy here. Okay? So what is the answer? 28 is wrong. It's a good guess, but can anyone correct that? All right, if I tell you the answer, you've got to tell me why. Okay? That's the deal. The real answer should have been 14. Can someone tell me why it's 14? It's a bit odd, isn't it?
Because the SRAM is mapping all the data in 16 bits.
Correct. Yeah, the SRAM is addressing 16-bit words, so it's only interested in what particular word number are we up to, and the answer would be 14, because it groups them in 2, so it's only looking at 2 bytes as a word. So if you increment the address, it's going to go up by 2 positions in your memory. So we have to divide that by 2, and what that really means is we're throwing away the lower order address bit, which is 0 anyway. Okay? So we've got to send a 14 to this device. So at address 14 in the SRAM, you're going to see this 16 bits, which is the 5555 hexadecimal. All right, so out pops. So we're now doing a read cycle on the SRAM. So SRAM dequeued the data lines from the SRAM. So the SRAM's actually responding with data after the access time, and that data is going to be this 5555. But its access time may be a bit slower than a clock cycle, and that's fine. Now, when we're doing all this, we're going to keep track of where we're up to, and the first stage is going to be stage 0, which is corresponding to the low order 16 bits. And then we want to say, okay, let's change now to the upper half of the 32-bit word, which is the upper 16 bits, which will be this guy here. So that stage variable is the flip-flop output that we just talked about earlier, and that works just fine. Okay, so The second half of this cycle occurs where we issue address 15, 16, 17 or 18. Which one is it? 15 is correct, thank you. Alright, so that now accesses the upper 16 bits, so that should appear in due course on the data lines. Okay, so what your logic needs to do now is to work out that this 555 goes to the low order 16 bits and this AAA goes to the upper 16 bits of the read data. All right, and it would make that decision based on looking at the stage variable. All right, very simple. And then we are complete. Let me just check one little thing. Okay. So we complete this by asserting our acknowledge 1, which you see happens there on the big dot. So in terms of the logic, you can see now that you can derive the acknowledge signal very simply just from copying the stage variable or the flip-flop output. So that just tells you when you've finished as well. So that will go back to 0 then after that clock edge. Okay, any questions on that? So what we've looked at now is roughly how to design this interface. So the next exercise we should be able to do very quickly because it's the store instruction now using the same address, which is 28. 20 plus 8. Okay, so let's just run through that pretty quickly. So we have the address lines coming out, so that is 28. Bus enable. So we're now going to write, so it's going low, and then the byte enables. That's a word, so that's full 32 bits. And then the write data is the point of distinction here that's different. And we see that in R7 we're going to assume we've got A, B, C, D, E, F, 0, 1. So the write data will reflect that. There's a 32-bit value that comes out. And that is fixed until the acknowledge signal is asserted. Now we're going to have to do this in 2 bytes, so we don't expect the acknowledge to come out until the end of the second byte as a 1. You have to set it up at this point so it's ready for the second clock edge, so that's fine. And the address now that the SRAM receives is similar to before. So we would do 14 followed by 15. But now we're going to write into the SRAM and we're going to write with the same signals that we used for read. So now the SRAM has to tri-state those signals so they're not driven, and the bus interface logic now drives into those signals to achieve the write in terms of 2 16-bit halves. Okay, so what do we expect to write first time? EF01, correct. And then we would follow that up with ABCD. And then it would go tri-state. Okay, we don't want to override any read actions later on. Okay, and the stage is exactly the same. Okay. Any questions on that? Right, so that's quite simple really once you understand the way it works. So let's just briefly look at the arbitration problem that we have in the setup of the FPGA. That's the blue area that you see here. So inside the FPGA, we're going to have two NEOS processors. And they both want to access the external SRAM that you've just been talking about. And the way that works is very similar to what you've done already, but we have two internal Avalon buses and bus bridges. So we've got bus bridge 0 for CPU 0 and bus bridge 1 for the other CPU. And they then go through your arbitration logic circuit, and that talks to the SRAM controller to issue the appropriate signals to the actual SRAM chip. Okay, so that looks pretty simple, I would suggest. There are some subtleties about this. So the JTAG needs a hub, so you get responses from both CPUs. You need to resolve that appropriately, so when you're looking at it, you can look in the right sub-window which CPU is responding. But you can see the details of that in the lab. All right, so if you understood this, you should be able to answer these basic questions. So we have an arbitration logic circuit, an arbiter. So it has two request lines. What are the names of those signals? So look at this diagram and tell me what the name of the request lines are. Now you've been using these signals, sure, on a single CPU, but it's the same name. All right. Bus enable, yes, but there's two of them. What are they called?
0 and 1.
Yep, good. So that's bus enable 0 and 1. I think it's... All right, so they're actually coming out of this external bus bridge. All right, so it has its own signal names, and it's going to be number 0 for the left-hand side and number 1 for the right-hand side. So once the bus enables are asserted, you're really saying, I want to access this shared memory, please give it to me. All right, so what are the acknowledge lines called? So this is your arbitration logic's going to issue an acknowledge to tell the bus bridge, yes, you can access the shared memory. What's the name of those signals? Again, it's the same as what you've been using. Yep? No, we've done the bus enable, that's the request. Acknowledge 0 and acknowledge 1, is that correct? Who thinks that's wrong? Excellent. You're right. Acknowledge 0 and 1. Sorry, just lost that. So acknowledge 0 comes from the bus, from the arbiter to the bus bridge. Okay, so we have acknowledge 0 and 1. All right, so that's just the same acknowledge lines that we're just talking about, but for separate bus bridges. Okay, is it asynchronous or is it asynchronous? Do we have a common clock in this circuit, or are these two independently clocked? It's common, actually. It's the 50 megahertz clock. All right, so that makes this whole thing much simpler for you guys. So everything is then synchronized to that clock, and it works perfectly. There's no metastable problems here because everything's tied to that clock. So what arbitration policy